out here today. We are Peak Engineering, and this is our integrated design project final presentation. So in week one, we received a brief and we also met our client. Our client is Good Shepherd Services, and the project is an extension to their facility at Edel House in Cork's inner city centre. Edel House operates as a refuge for unhoused women and children. At the minute, they have currently 50 spaces, however they are totally oversubscribed. So they've taken a decision to employ us to build an extension to their current services. The current extension will increase their capacity by 100 spaces and will also change the use of their facility to a refuge for unhoused women, men and children. The site is located, as I said, in Cork's inner city on the Middle Parish Island, which is enclosed by the Lees North Channel to the north and the South Channel to the south. We also received in our brief a set of architectural drawings. We began firstly by coming up with a method or a process by which that we could go through and emerge victorious with a good design that would be suited to our client. We began, as I said, with the architectural drawings and the brief. We came up with framing options and then off our criteria then we chose the most suited framing option to our client's needs. On from our framing options, my team would then speak about what we've done then. Becky would speak about the structural analysis. We looked at our framing option, we carried out a structural analysis and we emerged with bending moments, which Conor will speak with them, which we used to design our RC elements. From our RC elements, we had our final loads, and Nathan will speak about the geotechnical challenges of the site and our foundation design. Finally, James Beery will speak about how we tied everything together and produced outputs that will be suitable for industry. I'll hand you over to Becky now to talk about structural analysis.
Thank you. Good afternoon, everyone. The building is a 4-story building, and the loads that are acting on the building will be the vertical loads and the horizontal loads. The vertical loads will be the permanent loads and the variable loads, which the permanent load will be the self-weight of the slab and beams and columns, and the variable load. There's an area in the first floor that is there will be like a physical activity, like a gym. So we take account of that, and we took a variable load of 5 km per meter square on that floor, and the other floors will be we took a variable load of 2 kN per meter square. As you can see, the vertical load path, the self-weight of the building components will act on the slab, and from the slab it will transfer to the beams, and from the beams to columns, and from columns to the foundation, and finally it will be resisted for the with the soil of the ground. So the horizontal load, the horizontal loads will be the wind load. We assume that it will be 1 kN per meter square acting on the building from each phase of the building. So So the horizontal load path will be when the wind is blowing from the face of the building through the connection of the windows. It will transfer to the slab, and slab will act as a diaphragm and take these loads to the lift shafts and the stair cord. And we designed the lift shafts and the stair cords to resist these loads and transfer to the ground, and it will be resisted by the foundation and ground. So we also take the load combination for different spans of the beams and slabs, and we add like different load factor for the live load and the dead load to produce the maximum bending, hugging moment and the maximum sagging moment in order to for the design of our beams and slabs later on. We use the moment distribution method for this. Basically, it's a principle that is locking and unlocking of the joints in order to let the moment to be distributed and balanced at each joint and equilibrium. So basically, for example, we take one tree span of the beams, and we assume that one side is fixed and the 3 other spans are bent, and then we apply we assume that all are fixed, and then locking and unlocking of each one, and we try to get balanced moment at each joint. And then we produce a bending moment envelope. As you can see, it will give us the maximum hugging moment and maximum sagging moments. Then we will use these later on in our design for the slab and beams. And also we will use these, we use this and match it with the program that we use as a Line Pro program to check if our calculations are correct. And now I'll pass over to Conor Wright, who is talking about the structural design.
Thanks very much, Becky. So I'm just going to talk about the reinforced concrete elements of the design. So we were tasked with completing a design for a slab, a beam, a column, and finally a foundation or pad design. So starting off with our slab, we use the loads and moment distribution that Becky just talked about, and this is just the model of our building. So we worked out the loads and we got an area load, and considering it was our first time designing a piece of reinforced concrete, we tried to keep it simple but yet effective. So we came up with a 200mm deep, one-way solid spanning slab. Following on from this, we got the area load and the self-weight of the slab, and we designed our beams. Our beams were 300mm wide by 400mm deep, a square reinforced concrete beam which contained shear links and reinforcement to resist tension. Then Becky just spoke a bit about the load combinations. We used that as well to design our column to create the biggest moment in our column. And following on from that, we designed a 350mm by 350mm square reinforced concrete column. Again, this had shear links and reinforcement. At this point, we calculate the total load takedown, which was going to be transferred to our foundation. And from that, Nathan will speak a bit more about that in due course. Throughout this process, we also had close consultation with the client. So it was our duty to outline to the client its roles and responsibilities. So that was, for example, that the client would only appoint competent professionals that were well capable of carrying out the job or the task they were appointed to do. Also, it was the client's role to appoint the right various personnel. So us, the designers, but also the project supervisor design process, and also looking at the construction stage to follow the project supervisor construction stage, and also the contractor to carry out the job. The client also had to contact the Health and Safety Authority due to the scale of this project, for both on the commencement of the project, but also if there are any accidents or injuries do occur on site. We also encourage the client to be proactive throughout the project, because they are the control and they are the person with the most control of the project, and they're going to be the end users of the building as well, so we want to maximise their benefit from the project. Looking at ourselves, we had to also upskill throughout this project. For example, surveying, we learned how to do topographical land surveying, but also levelling exercises as well. And we presented then this information through learning how to use a package called AutoCAD, and this is how we presented most of our deliverables, which James will talk about a little bit later on. So just relating back, we had our final load takedown from our columns. I'm now going to pass it over to Nathan, who's going to discuss how we transfer this into foundation design.
Thanks very much, Gareth. So as Gareth said, I'm going to go through the geotechnical aspect of the design and some of the challenges that we met along the way. And for those of you who aren't geotechnical enthusiasts, I won't go into too much technical detail, but basically we're concerned with the bearing capacity and the settlement. But before we go into that, we're just going to go through some of the other issues we met when dealing with the site. So some of you know Cork City is built on a river. It's actually built on the estuary of that river, so the soil on site is going to be deposited over years of just building up and building up, so we expect some natural consolidation from that, but because of its city centre location, we're expecting that some building at some stage in its history would have been put on it, so there would also be some over-consolidation to be expected. Now it's a medieval city, so we're specifying that an archaeological survey should be carried out prior to construction commencing, so as to not to have any delays during the construction process. Also, it is good to mention that flooding is to be expected. It is very close to Mercy Hospital in Cork, and as some of you may remember, that area was flooded very badly in 2009. So to get started, we were given a borehole log. This was a result of a survey consisting of 3 boreholes that were carried out on the site. So we could use this to give us a general idea of the ground profile, consisting of a soil profile. As you can see from the borehole logs there, you have the different layers of material, and we had 3 of them, so we could put together an attempt at a 3D soil profile. We also were able to use the Annenberg limits and the in situ moisture content to give us an idea of the consistency of the soil. And we could also use the standard penetration test values to give us an idea of the initial bearing capacity. And we could put all of this information together to give us an idea of the ground profile. So then moving on to bearing capacity, there was 2 approaches to estimate it. One was through laboratory tests, such as the direct shear or triaxial. Now the triaxial test is imaged there. And also we could use correlations from the borehole data, such as the standard penetration test and the cone penetration test values. So these results were tabulated here, and as you can see, there's a massive variation in the laboratory results. We're going to go through why that is in a moment. But from the borehole data, boreholes 1 and 2 were consistent, and the cone penetration test was consistent with those values. However, there's an outlier in borehole 3, and we're going to go through in a second now why that is. So the laboratory issues we said were as a result of using reconstituted soil. So soil that was available to us, it wasn't from the site, and we made it up by adding water and compressing it in a mould. So there's quite a large margin for error there, there's substantial error. And also, it was our first time doing these tests. We are experienced with the whole process. And then borehole variations, where we say that the outlier came from, is that there's actually there's a strata of soil that doesn't go the whole way across, and only borehole 3 picked up. And without further investigation, we cannot assume that that is a localized area, and so we have to design to the softer clay bearing capacity, which was 30 kPa. So this goes then on to settlement, so we have two issues: how much is going to take place and how long is it going to take to get there. So to find this out, we did an odometer test, which is where you apply a load to the soil and you measure its displacement over the course of time. And this led to a total settlement of 380 millimeters with a differential settlement of 140 and a time for 90% completion of 9.5 years. Unfortunately, this is far too much in both cases. Differential settlement is far too large, it's taking too long. So some of the proposed solutions are with drains, which are imaged there, which are basically pipes that go down through the soil and they minimize the distance the soil has to travel, or the water has to travel to escape the soil, and also surcharging the soil, which by putting a large layer of soil on top of it to help get rid of the water prior to construction. So this leads us then to foundation design, which is where we use the takedown loads that was calculated during the design process, and divide that by our allowable bearing capacity to give us a foundation area. Now this was too large for the pad foundation, which we had designed for in ORC masonry, so we were saying from a soils perspective, a RADS foundation should be used. And with that, I'm going to hand you over to James Beery, and he's going to go through the outputs.
Thanks, Nathan. Okay, so just go back over the whole design process that we went through from beginning to end. We started off by comparing and contrasting and then choosing a scheme. We estimated loads that we acted on each floor. Using different packages such as Linpro and other methods such as moment distribution, we analysed each member and calculated the moments and forces that we acted on each, which could lead us to fully design and calculate the reinforcement that was needed and the depth of each particular item. So once we had the slab, beam and column designed, we could calculate the total loads that we acted on our foundations. Using our soil data, we estimated bearing capacity and hence designed a foundation. Once we had the full building designed, we had our 4 main structural members completed. We had to think about how we would represent this information and how we would deliver to a contractor so it could be construction on site. So the main outputs that we came up with were a bending schedule, a construction process, and AutoCAD drawings that contained scheme layout drawings and reinforcement drawings. So the first was a scheme layout drawing, which is just, this is a plan of our foundation setup, which just shows the plan area dimensions of each foundation and the distance between each. This section through that foundation drawing, which shows the depth below ground that the foundations are laid at, the amount of backfill required, and also the slabbed column interactions. The bending schedule contains the amount of reinforcement required in each individual member, the diameter of the bars used, the number of bars, the shape code and just dimensions of each part. A reinforcement drawing then just goes hand in hand with the bending schedule to show where each bar is located, and lap lengths and anchor lengths all included there. One question we were left to ponder with coming towards the end of this project was the geotechnical aspect. We were wondering, are geotechnical factors of safety excessive? We spent weeks doing laboratory tests on our soil, using empirical data trying to get a bearing capacity. Once the bearing capacity calculated, we then used a load factor of 3, which is to design the bearing capacity that we'd use for our model. And we're just wondering, I mean, it's a lot to go through to then just put on sort of what we thought was a large load factor on, and then design with that bearing capacity. I'd like to leave it at that and open the floor to any questions you might have. Thank you for coming.
Your concrete scheme design was very well illustrated with beam and slab. Did you consider alternatives to that, and why in the end did you choose the beam and slab?
Yeah, I suppose we didn't consider flat slabs, but it was just our first time designing a reinforced concrete structure. We just tried, even a beam and slab was working and it was efficient in that slab range. So